Ever think of your refrigerator as a chemistry lab? Right next to your salad dressing, you likely have the ingredients for a working chemical test kit sitting in the vegetable drawer. In chemistry, we use things called color indicators. These are specific liquids that shift their appearance to reveal the hidden nature of whatever solution you've just mixed them into. Look at this diagram showing how it works on a tiny scale. You have an indicator molecule here and an unknown molecule there. When they meet and lock together, they react. That reaction causes a sudden, bright color change, showing us properties we couldn't see before, like how acidic the liquid is. To perform these tests, scientists generally have two options to choose from: synthetic indicators made in laboratories and natural indicators derived directly from plants. You can see the formal approach in this laboratory setting, where scientists use specialized synthetic chemicals in precise glass tubes. But you could also see a clear reaction right at your kitchen table by using the juice from a red cabbage. Both the lab chemicals and the cabbage juice achieve the exact same immediate result. However, the origin of those liquids sends them on very different paths once the experiment is over and the liquid is poured away. Professional chemists often lean towards synthetic indicators for a very practical reason. They are easy to work with and reliably produce a sharp, distinct color every single time. But that reliability comes from industrial manufacturing. This refinery shows where that process begins. Synthetic indicators are made using chemicals derived from petroleum. Turning crude oil into a specialized laboratory liquid takes a massive amount of processing, and making these petroleum bases can release pollutant gases directly into the air. When the work is finished, if these synthetic liquids are washed down the drain, they travel through our plumbing into local water systems. This chart shows how these artificial molecules behave over time. Because they aren't found in nature, they don't break apart. Instead, they just stay there, stacking up in the riverbed year after year. You can see the impact where this wastewater meets the river. When these indicators build up, they pollute the surrounding soil and become toxic to the fish and other life trying to survive in that water. The perfect, crisp colors scientists get in the lab come with a hidden trade-off. To achieve that exact measurement, we introduce permanent materials into the world that nature cannot handle. We do have an alternative. Instead of using petroleum, we can extract indicators from everyday plants, like crushing up berries or boiling that red cabbage from the kitchen. When you pour a natural, plant-based indicator down the same drain, the journey ends very differently. Because it comes from nature, it is entirely safe for the surrounding environment. In this diagram, you can see how the environment handles plant-based indicators. Tiny microbes in the soil and water recognize these materials as food, pulling them apart into harmless organic shapes. Because the environment can digest them, natural indicators leave nothing behind. They keep the soil clean and are non-toxic to aquatic life. The drawback is purely a matter of accuracy. Plant-based liquids are less precise. On the right side, natural indicators produce bleeding, blurry colors, which makes it difficult for chemists to get an exact reading. Relying on plants keeps our rivers and soil healthy, but it means researchers have to accept results that aren't quite as sharp. Every time a chemist prepares for a test, they have to weigh these two options against each other. This scale shows the choice. On one side, perfect accuracy that leaves toxic residue. On the other, safe plant-based liquids giving a softer result. Scientists must decide what the job requires: absolute precision for new medicines or eco-friendly indicators for routine checks. Modern science is about more than just finding an answer. It's about taking responsibility for the tools used to find that answer. The next time you watch a liquid change color in a test tube, think about the full cycle. Ask what that color shows you right now and where those chemicals will end up long after the test is done.